Okay, great. So my name is Yuvraj Agarwal. I'm from UC San Diego. This talk is really about an application and how we've used Zen in a way to actually make PCs a lot more energy efficient than they are today. So today I'll present SleepServers, which is basically a software-only architecture to reduce the energy consumption of PCs in an enterprise environment. So we all know power and energy efficiency have become key drivers of designs of devices. And if you look at battery-powered devices, it's very clear you want as large a battery lifetime as possible without having to actually have to recharge the device. Interestingly, energy management and improving energy efficiency has become important even for wall-powered computers. So stuff that is plugged into the wall, such as servers, desktops. And while a lot of people are actually talking about the server power consumption, it turns out even desktops consume a lot. And just to give you an idea, you can have a desktop power consumption can go from a watt when it's in a sleep mode to almost 140 watts plus when it's completely active. And of course, the goal in this case is how do you reduce the amount of money it takes to power up these machines. So even though these two classes of devices are very different, the overall goal in terms of energy efficiency is how do you do more work for less power and energy. Now, even though it's a well-known fact that PCs actually consume a lot of power and IT equipment is starting to dominate in terms of the total energy consumption, according to some estimates of almost at 7% of the total US energy consumption, shutdown opportunities are really very rarely used. In fact, longitudinal studies at Lawrence Berkeley Labs, including some of our own data, have shown that almost 2/3 of office PCs are left on, even after work hours, even when people are not there. We all hope people are more productive and they're working over even on the weekends. But lots of the times, these PCs are actually not in use. Now, you could argue that at workplaces, the person who's using the PC is actually not paying for the energy bill, so maybe the motivation is all wrong. Interestingly, even at homes, where people actually pay for the energy use themselves, people leave their PCs on for a long period of time. We've actually confirmed this in our own department. We're a computer science and engineering department. We have lots and lots of computers. So interestingly, using network-level techniques, we found out that about 90% of our PCs are actually never turned off during nights, weekends, etc. So we actually tried to dig deeper to find out why, what's the main reason why people do not turn off their PCs or utilize sleep modes, even though they've been available for almost a decade or more. Turns out there are several reasons. The primary one is, users have this nitpick about, I want to maintain state. I want to make sure my desktop is the way it is. I have all my applications open. I have all my environment set up. I don't want to have to recreate it if I have to wait for Windows or whatever OS to boot up and I have to open up all my applications again. So be it. Then there are these other applications, which are actually a little bit more interesting. They fall into two categories. The first category is occasional access. So you want to make sure that you can remote into your machine. You can access SSH. You have some file shares set up. You have some network shares set up. And for that, all of these requests are necessarily asynchronous. You don't know when you want to access, and that's why you might have to leave your PC on. And for a lot of administrative reasons, patches, updates, etc., which can happen at any time of the night. And then the third class, which is examples of applications which by definition are such that they're active applications that are run necessarily in the background, even if the user is not present in front of the PC. So examples include, you're trying to maintain presence over your Skype and you're logged on because you might be in the other room or something, but you still want to maintain presence over Skype, or you're trying to do a long-running application such as a web download, or even though most people won't say it, about 50% of our respondents said that they actually participate in BitTorrent and peer-to-peer at home, and that's why their PCs remain on at night, because by nature, this is altruistic. I need to serve out data even when I'm not necessarily downloading anything in the night. The first, that is maintaining state, can actually be handled by current sleep modes. You routinely put your laptop to sleep, and then when it comes back, it still maintains state. But the occasional access as well as actively running applications cannot be done in current low-power sleep modes. So if you look at it, the problem really is rooted in the way PCs are sort of currently designed. So current PCs are either awake, in which case they're fully active, or they're sleeping, in which case they're necessarily inactive. What happens, though, is a PC, when it's active, takes 100 watts, even when it's doing nothing, right? It's like it's idle, or that power goes down to 1 watt when it's sleeping, but in that state, it really can't do anything. So you see this dichotomy. I can use 100 watts even when I'm doing nothing, or I can use 1 watt and save power, but I can do nothing in that state. But from the perspective of the network, the assumption is that the PC is always on, the host is always connected, for the myriad of reasons I just talked about. What you really want is a way of, making a PC maintain functionality as if it was in a fully awake state, except it's consuming power only as if it was sleeping. So remember, there's almost a 100x difference in terms of the power consumption in these two states. And of course, you could resume to a fully awake state and use that 100 watts only when needed. And all these other states, you're in this sort of hybrid state of operation, which is sort of fundamentally trying to change the distinction between what you can do in a sleep state, what you can do in an active state. So the first approach we actually looked at to do this was to try to see if we can augment the PCs themselves to enable this hybrid mode of operation. And our objective is, how can we make PCs responsive even when they're asleep, maintaining availability across the entire protocol stack, which means responding to low-level requests such as ARPs, pings, et cetera, as well as maintaining availability across, replying to application layer requests, waking up the PC if you need SSH, or even doing applications on your behalf. And we want to do this without any changes to the network infrastructure or adding more and more components. So as I just told you, a PC, when it's active, takes about 140 watts. This is when it's actually consuming data. This is just one PC. When it's idle, it takes about 100 watts, and then when it's sleeping, it drops down to about 1.2 watts. Our solution to this, the first cut, was can we actually augment these PCs with a very low power secondary processor that has a low power CPU, has some memory, has some flash storage, and the secondary processor sort of forms a separate domain, and this secondary processor can then sort of proxy on behalf of the host when it's sleeping and effectively masquerade at it as the PC itself only when the PC is in a sleep state, and then can disappear when the PC comes back to a fully awake state. Of course, in order for all of this to work, you want to make sure that the secondary processor is very, very low power. It's functionally similar, so it should be able to do and actually effectively masquerade as the PC, but it should be like almost less than a watt. So our power point was, several hundred milliwatts to maximum of a watt. The natural place where you like to put this would be on the network interface, because if you noted, a lot of these applications were very network facing, but you can really have it at any other place on the PC. So since we were building PCs that talk in their sleep, we called our architecture Somniloquy, which means sleep talking, and this actually appeared at NSDI last year. And in our case, the secondary processor was on a separate power domain. It's on when the host PC is a sleep state. It has all the components that I just mentioned, processor, memory, flash storage, has an embedded network stack, and has the same MAC address, same IP address. So to everybody else, it looks like the secondary processor is really just the PC itself. Additionally, for certain apps, you actually just want to wake up the PC. So if I'm trying to remote desktop into my PC, I don't want to remote desktop into my secondary processor. I actually want to get to my PC. So for that, we have this concept of very configurable regular expression wake-up filters that you can set to wake up the PC. And for a smaller class of apps, we can actually handle them even when the PC is in a sleep state. And we handle them using this concept of an application stub. So the first class of apps are ones that do not actually maintain any per application long-running connection or any state. So they're essentially stateless. And the way we handle them is, you can specify, the user can specify, or a lot of these filters can actually be gleaned from your firewall logs or the status of applications that are open. And you can specify saying, I only want to wake up on an incoming VoIP call, or I want to wake up on a remote desktop request. And I'm sure a lot of you have heard about Wake on LAN, right? And I just wanted to spend a few minutes on, less than a minute on why Wake on LAN doesn't really work and doesn't really solve it. It's been around for almost 10 years. The problem is that Wake on LAN hasn't really been adopted because it's either too impractical, because it says that, hey, you need to send a special magic packet that has 16 copies of my MAC address. You need to be in the same subnet that I'm in. And then the question becomes, who sends this magic packet? And if I'm trying to do Skype or something, how do I get this magic packet in the first place? Or you can make it much simpler and say, hey, wake up for any packet that's meant for me. That means, in certain cases, even broadcast packets will wake you up. So it leads to either you just don't sleep enough, or it's just too impractical to actually get it to work. And never mind, you really cannot run active applications anyway. So in our case, these wake-up filters can be specified at any layer of the network stack. You can say, fine, for a wireless version, you can even say, wake up my laptop when you see a particular Wi-Fi network, or do anything on my behalf. So the second class of apps are ones that are stateful. And examples include, for if you're doing a long-running web download, or you're doing BitTorrent, or participating in other peer-to-peer networks. Now, for each of these apps, I actually need to understand how the protocol works, because I can't just say wake up the PC, because you'd be waking up the PC too often every time you're sending a packet on these networks. So for these apps, we actually need this application-specific code running on the secondary processor. Now, this is quite challenging, right? Just from the get-go, I said the secondary processor is going to be low power, has a small amount of CPU, smaller memory, et cetera. So really, I cannot fit the entire application. So our solution to this problem was to offload only parts of the application that you really need, and we call that a stub code. Basically, that means if you take up an application and you strip out all, so remember, the secondary processor has no graphical user interface or has no way of a user to interact, so why not just take away all the GUI components? Why not take away everything except just the protocol? Now, trying to do this automatically is pretty hard, as we've realized, and we have a project going on which looks very promising. So given an open source application, trying to create these multiple versions of apps for different architectures and creating these automatic lower power versions. But just as a proof of concept, I actually created stub code for like 5 different applications manually. BitTorrent, background web downloads, multi-protocol IM, so you can participate and maintain presence over several IM networks, just to show that this is actually indeed possible. So this is what our prototype looks like. I have one, just to give you an idea. It's not really that big that's shown in the picture. This is just an initial prototype. It has a low power processor. This is ARM-based, so it's neither Intel nor AMD, so hopefully I'm not upsetting anybody. I'm sorry? Well, you know what, 200 milliwatt, if anybody can get me 200 milliwatt, I'll go there. And it has a flash memory, so you can store applications and store application data. And then we have, the reason why we built it over USB was that I really don't want to leave everybody who has a PC right now out in the lurch. So as long as you have a USB port, we're basically adhering to how USB works, and we can wake up the PC over USB, we can detect its status, we can transfer data, everything over USB, and get power even when you're in a sleep state. Turns out that's actually very feasible too. We have a wireless prototype. So we had results even for desktops, but I want to show you what a laptop number would look like. So you have a laptop in sleep mode, which gives you about maybe 88 hours of battery lifetime. Compare that to a laptop in normal mode, you get about 4 hours of battery lifetime. The baseline is when I've enabled all the power management features. I've turned off the screen, I've turned off the backlight, I've turned off extra radios. Basically, my laptop was sitting there, but if an email would come in, it would wake up. I get about 6 hours of battery lifetime. You compare that to the sleep talking mode of operation, and you get almost a 10x improvement in energy, in battery lifetime, because essentially you're getting the power consumption close to sleep mode, except you're getting some of the functionality as if you're fully awake in the baseline state. So, and similarly for desktops, I haven't shown this here, but we've collected sample traces for 24 different desktops based on their usage, and we found out basically we can save about 38% to 85% based on the particular use patterns. Now, this is all great. So I said, hey, if it's such a great architecture, we got lots of press, lots of people interested in it. So he said, hey, let's try to deploy this and see if it can work in an enterprise. I went down to my system administrator, and he said, well, for individual desktops and laptops, this is great. For mobility, for laptops, it's perfect. But have you thought enterprise environments are a little bit more challenging than that, right? So adding hardware to each PC, the first thing they asked is, what is the bill of material for something like this, right? I said, well, about $50, maybe we can get it cheaper. The cost is, okay, fine. So we have this individual hardware that needs to be added. Let's say we can figure out how to make it much smaller. But then there's these added costs. This is like the administrators really do not want desk side visits. If suddenly my PC doesn't wake up, my administrator gets called saying, hey, what happened? What did you do? What is this new gadget? I need to patch this. This secondary hardware is running some code. Who patches this? Who maintains this? Have we just suddenly opened up a whole new plethora of problems, right, that weren't there before? So the question that we wanted to answer is, can we actually try to get this sleep talking functionality without this constraint of adding hardware to each PC? Remember, we're looking at enterprise environments where the assumption is that PCs and servers are fairly static. They don't move around. And the answer is yes, we can. Just need a little help from the network. And of course, the reason why I'm here is because we actually prototyped it first using Zen. So the main idea here, and the architecture that we've called is called SleepServers. And the architecture looks as follows. So let's say you have lots of host computers. They can be on different VLANs, whatever. You have H1, H2, and maybe host 100. Each host has a particular MAC address and an IP address, as I've given. H1 has MAC address, MAC1 and IP1. To this network, you add this dedicated sleep server machine. And you could have scalability. You can have more sleep servers. The sleep server has an image M for each host that wants to participate in the SleepServer functionality, right? So the ImageM basically mimics exactly what the Somniloquy daemon would have done, the Somniloquy piece of hardware would have done. It has the same MAC address, same IP address, and of course only one of them is going to be on at any one time because you can't have more than one, the same MAC address appear at two places. And similarly for H2, you have a corresponding image M2. So the good part about this is that now you can think of the SleepServer as a collection of hundreds and possibly even more of individual Somniloquy pieces, except that now I can dynamically scale up and scale down, give image M1 more resources than M2, which I really couldn't do in Somniloquy. You got so many MIPS that was on the secondary processor, and that's it. Whether or not you were just responding to pings or you were actually doing downloads. So in this case, I can actually give you more capabilities than you had before. And the biggest part, of course, all of these images are in software. So the main idea is that when host H1 goes to sleep, its corresponding image M1 becomes active, and then there's ways to figure out how only one of them remains active, and then M1 can do all the tasks that the Somniloquy hardware would have done. It can reply to network requests for you. It can wake you up if there is a particular request that it cannot handle. If there are application stubs for the particular applications you care about, it can run those applications, and then we can scale up very well. So there are lots of attractive features now that SleepServer brings up, right? First, it can be implemented on commodity server hardware. It can simultaneously support many, many hosts. There's a single point of management, and you can have redundancy. You can have two SleepServers, or you can scale up as and when required. And most importantly, there is no hardware additions required to end hosts themselves for enterprise environments. But there's lots of challenges to overcome that I'm not going to be able to cover in this talk today. There's enterprise networks can be pretty complex. There is lots of different networks, multiple layers of switches. There's immense heterogeneity in terms of operating systems, applications, configurations that everybody has. Especially if you look at an enterprise like UCSD where everybody runs their own thing, it becomes pretty complex. And scalability, I said you can support lots and lots of hosts. The question is, how do I scale? Is it 100? Is it 1,000? What can I actually get to? And of course, questions like, how do you make sure the images are safe and you're not opening up other security holes? So just to give you an idea of a machine using SleepServers, you would start off at about 100 watts. This is actually my PC. If I had internet, I'll actually show you the power trace for this PC. Even if you enable all the power management features that were there, so this was a dual-core Intel machine. I turned off downloaded an Intel utility, turned off the other core, put the processor in the lowest frequency possible, and then still I reached to this base power, which is basically what I cannot do better than that. And that was about 93 watts. And if you compare that to using SleepServers, you get to about 2.3 watts. So assuming a 45-hour work week, this is not the typical work week of a grad student. We hope they all work more than 9 hours a day. But you're lazy, you only work 45 hours a work week. That translates to about 620 kilowatt hours. And in terms of California prices, which is pretty low, this is about $60 plus of energy savings. And these are multiplicative, right? You have 1,000 PCs, suddenly you're seeing a lot of savings. Now, the important part also is your PC is sleeping. So for all the application layer requests, it needs to wake up, right? So there's additional latency, right? If you're trying to remote desktop, there's additional latency. And we picked desktops that are about 7 years old. So lots of people actually have very old desktops in our department. 2 desktops that are pretty new. And we basically saw an increase of about 3 seconds to 10 seconds, additional latency across a suite of applications. And the fact is that if you look at modern OSs, they're getting much more better than this. So a lot of this latency is actually dominated by the time it takes Windows to come up and for the Windows network stack to come up and start responding. And we're hoping that this is going to be much better. And to be honest, this latency is only an initial setup latency. Only when you have the incoming call or only when you have remote desktop, it's an initial setup latency and it's amortized over the length of the entire session. This is what trace using SleepServers or without SleepServers would look like. The gray line, which is a little right at the top, shows 2 weeks worth of data where I wasn't using SleepServers, and after that, I did start using SleepServers, and basically my usage became very on demand. Whenever I needed something to happen or whenever I tried to log in or something, my machine would wake up. And this translates to about 68% energy savings. Let me show you across a suite of users. So think of this as a step function. S denotes the host is sleeping, and the sleep server image is enabled, and this is 2 weeks worth of data. And A denotes the host is actually active and its corresponding sleep server is disabled. And this is and we've deployed it. Actually, we now have about 50 plus users in the department. But I've just picked up a sample set of users. You add 7 more users, and you start to see quite a bit of diversity in people's usage patterns. When they come in, when they go, there are some people who don't look like they work very much. PC8 remains asleep for most of the time. PC1, it looked like he works quite a lot, but it's really a web server. So every time somebody hits a web page, the machine actually wakes up. So, and what we also did was for the first week, we told the users that you're responsible to turn off your machine. Put your machine to sleep or to sleep server mode. And for the second week, we says, hey, here's a policy. In 30 minutes of inactivity, we'll put your machine to sleep automatically. And of course, remember that if you needed access to it, if you had something running, you can actually do it anyway. So you see there's lots of differences. PC2 and PC3 users actually forget often to put their machine to sleep over the weekend, versus the next week it starts to get much more controlled. And then PC6 and I believe PC4 are ones that actually do remote desktop quite often. There are people who actually run wrong running downloads. We even found some people that did BitTorrent, for example. So what are the total results? Across all our users, we see about 30% to 85% energy savings. The average energy savings are 70%. Automatic sleep timeouts, of course, enable better savings because it addresses the fact of, oh, I forgot to put my machine to sleep, or today I went out to 2-hour meeting and didn't realize that I didn't put my machine to sleep. The third class of apps that I mentioned was ones that you can actually do statefully, right? And I'm showing you a trace of a background web download application. So the gray line shows the download if you were doing it on the PC itself, versus the blue line shows if you were doing the download using our architecture. So when you use sleep servers, your machine starts the download, and then the machine transitions to sleep. The download continues, and we just simulated that you only have 200 megabytes of storage on your image. When the image space fills up, it wakes up the PC, transfers over what it has, goes back to sleep. So effectively, just for this download, and we didn't pipeline, when you were transmitting, you weren't really continuing to download, you basically save about 92% for this download itself. And this is just to show that you can save a lot of energy even for active applications. So then, here comes the scalability question, right? What can you do? How many VMs can you support? So the red line shows basically the percentage CPU used when the VMs are all idle. They're really not doing anything, which is what will happen for when you have all these machines. Most of the time, they're really not doing very much. The green line shows the percentage memory used, and of course, it keeps growing up as you're increasing the number of sleep server images. The blue line shows the percentage CPU if you're starting a download stub on these applications, but they're just writing to dev null, so they're not really writing to disk, versus the pink line actually shows when you're doing the download and writing to disk. So, of course, there is limitations. And these results are several months old, and I've been active on the mailing list. I'm not sure how many people have been looking at our questions on. We started off with less than 50 because we ran into lots of issues where there were hard-coded limitations on the amount of images you could start up as. Currently, and when I was preparing for the talk, I was actually at about 155 and trying to fix a dynamic IRQ bug. Hopefully, we can get to even more than 154. The utilization is pretty low, even at that level. Of course, the major problem that we came into was if you have one disk. This was a single RAID 1 mirrored array, and if all 50 of them are trying to write to the disk, slowly the throughput on the disk goes down significantly. And our solution to this is actually use either a network-attached storage, or we're actually trying to use some faster flash disks and see what kind of performance would we get. Remember, they're not writing that much. And then also, if you had multiple disks and we stripe these images across a set of disks rather than everything hitting one disk at the same time. We'd be more than happy to learn how to scale the sleep servers more. And if you imagine that if I have 500 of these images, what problems I'm going to run into, I'd love to hear back from you guys about what I should do and what potential roadblocks I'm going to run into soon. So currently, we have, as I said, about 150 plus VMs on the sleep server. In terms of energy savings, one server is about 300 watts, and if you have a Nihilo machine, it's about 200 watts. each desktop is about 150 watts. So you can easily see the scale with the energy savings are coming. And again, we are cross-platform. I have Linux, Windows, and these are all just software-only additions to these PCs. According to our estimates, we get about 60,000 a year. We imagine these are the amount of energy savings we could get if we deployed SleepServer widely. What's interesting is this is just the energy savings for powering up these machines. So if you think about it, if you're taking 100 kilowatts to power up these machines, you're also, all of that is coming out as heat at some point or the other. So we're actually cooling all of that machines if you're in California. Like, I don't know what would happen if you're in the Northeast or something where you might want your PCs to keep your office warm. But in California, that's what we're doing. We're actually trying to cool all of that stuff. So idle cycles are actually costing us quite a bit. So just quickly to wrap up, we have a project at UCSD also called the Energy Dashboard, where we're trying to identify, okay, so how much of the total load of our building is actually IT, and we've actually instrumented the entire building, and we can break down the total energy load. I invite you all to see it. I'm not getting network connectivity, but you can go to energy.ucsd.edu, and we did a press release on this dashboard. My particular machine on SleepServers is actually online, and you can look at this use. Just to give you an idea, this is what our total energy use looks like for a week: Monday, Tuesday, Wednesday, Thursday, Friday, and then Saturday, Sunday. You can clearly see the the daily variations. At 6 a.m., the power starts to go up, goes up till about 5 p.m., and then starts to come down. Funnily enough, this base load of the building, which is 325 kilowatts, remains the same all year, irrespective of seasons. We actually even have a further breakdown. Black line shows the server power for the same week. The dotted green line shows the plug loads. And we're a computer science department. We pretty much only have computers plugged in. The purple line shows the lighting, and then the dotted red line is everything in the air conditioning. So meaning HVAC, fans, pumps, chillers, everything that maintains climate control. So if you look at this, it's a very interesting graph because it shows that IT load, especially if you add up during nights and then over the weekend, you see that everything else is duty cycled pretty well. Like the air conditioning, et cetera, goes down pretty well. But what doesn't go down, add up the black line and the dotted green line, this is IT load. Nobody or very few people actually manage their power consumption or put their machines to sleep or off, even when they're not using them. So it turns out duty cycling IT loads is actually essential to reduce the baseline. And this is what we're trying to do across the entire UCSD campus. I'm leading this effort to identify, where our what can we actually do to make our campus more energy efficient. Just some of the related publications in this space. I invite you to go to see the dashboard, energy.ucsd.edu. You can track my usage as well. And then I can thank you for listening. I can take your questions. Go ahead.
Hello. The mic is not, now it's working. Okay, thank you. Question. I just wanted to be clear. So the VMs that you're using in SleepServers are like stub, the same kind of stub.
It's very reduced functionality VM. It's not your entire desktop state.
It's like a manually constructed VM.
Yes,
okay.
And it's running a different OS, and it's the stub. It's running the stubs that you want. That's the point.
Okay, right.
Yeah.
Thanks.
And that's how you get. I mean, the important part is we're not moving your entire desktop state around, because otherwise we wouldn't be able to get this, couple of hundred VMs, couple of hundred images on the same machine.
Only exercise I'm getting all day. How does the role of your SleepServer morph in a virtual desktop environment, in a VDI environment?
So we actually just, interestingly, this paper is at Usenix. So we just got, our shepherd was also from VMware, and he asked us this question. So he said, he particularly said that even though the world is actually moving maybe to this virtual desktop environment, the scalability that we can get, and maybe I think they could coexist in a way that you could have the virtual desktop, but if your VMs is really not doing very much, then perhaps you want to have SleepServer along with it so that your actual backend servers can actually scale much better than if you were trying to move entire virtual machines on. So the point is that if you're trying, I have 4 gigs of memory on my desktop, right? I mean, if I'm trying to move all of that back to a backend server, I'm not going to get very much scalability at all. And yeah.
operational expenditure associated with the hardware. How about the software? The VM also has an OpEx associated in terms of maintenance, manageability.
Yeah, it does. What I meant was, in this, it's still much better. 'Cause this can be really a server in the administrator's cage, right? It's nicely managed. We're developing a very nice like a management console where the administrator can decide, hey, I want to enable this machine with the SleepServer or not. And I believe it's much simpler because they're much happier about doing it when it's all in their control and they have to minimize desk side visits. So the question is, how do you decide what's in the stub VM? The fact is that right now, only what we have stubs for can you have in the stub VM, right? So if you come up with some esoteric app that I don't have the stub for, unfortunately, we won't be able to handle you, right? That's the thing. So if you have applications that you care about that we have a stub for, that's what's going to go in the stub VM. Turns out for a lot of the apps, which are essentially of the type of asynchronous requests, so that I want to just remote into my machine or I have a file share, you don't actually necessarily need stubs. So we have a SleepServer Lite version for that.
Yeah. So regarding the point you made about moving the idle VMs to the server, you can actually balloon the VM to a smaller size, so that it's not that big of a problem.
But you're still doing, Windows is still churning away, doing something at the background, right? Even when you're, like it's not just, you're using unnecessary cycles when you really don't need to.
How idle the VM is. Actually, we have a paper at Usenix as well, so we can talk about this later.
Okay, sure.
Yeah, sure. Thanks.